Dear jury members, dear family, dear friends, I'm very glad that you could all be here today. And I look forward to presenting my thesis. As many of you know, I drive a very dirty fossil fuel car. And I hope that my thesis can at least compensate for some of it. Now, I'm not the only one. If we look at energy use today, the vast majority of it is still fossil fuels. In our final energy demand, the way we heat homes, the way we power industry, the way we organize transport, the vast majority is still not electricity, is still covered by fossil fuels. Only roughly 20% is electricity. And also in electricity generation, the vast majority of how we generate electricity is still covered by fossil fuels, and low carbon sources like renewables or nuclear still cover less than 50% of this. All right. This has, of course, dire consequences. We are facing climate change, droughts far away, but also in Belgium, floods far away, but also in Belgium, forest fires far away, but also in Belgium. The silver lining is that we know how to address this problem through renewables. And renewables really stand out as cost-efficient climate mitigation strategies. Renewables have really proven themselves as cost-efficient solutions, and this shows also in their growth rates of the past years. Their modularity has unleashed fantastic cost reductions. And we see this in the growth rates. All right. Throughout this thesis, throughout this presentation, I will often refer to solar power as PV because photovoltaics are the underlying technology. And as if climate change was not enough to convince us of the need for renewables, there's also very much energy security. Because again, earlier this year, our critical reliance on imported fossil fuels has demonstrated itself as a critical strategic vulnerability. But we know what to do. We know that we need to shift from fossil fuels as the main carrier and as the main source of energy to an electric system with electricity as the main carrier and renewables as the main source. And not only do we know that this is the road to take, that this is the road ahead, slowly we are also seeing that this is actually happening. The International Energy Agency, in its Global Energy Review of this year, sees that electricity demand is growing much faster than power demand, final energy use. And in electricity generation, renewables are growing much faster than other electricity generating sources. So bit by bit, we use more electricity as share of final energy demand. And bit by bit, we use more renewables to make clean electricity. So when we zoom out, what does this mean for Belgium? And some colleagues at Energyville have calculated what we would need to get Belgium to a net zero energy system by 2050. And by 2050, I'm only 53 years old. So this needs to go fast. We need a lot more wind power onshore, but also very much offshore. And this slide serves to show that the future of Belgian renewable energy is also very much at sea, offshore. Solar power, we need a lot of it. We are a small country. We need to organize our living space, agriculture, nature, all on a quite small plot of land. So covering more than the size of Antwerp by 2030 is doable, but certainly a challenge. We are starting to see a number of challenges, barriers occur to the growth of renewables. I have mentioned competition for space. We don't have a lot of space in Belgium. But there's also public opposition, and you all know this from wind turbines. People do not like these big machines in their gardens. But increasingly, also solar power is starting to suffer from this. Solar power is the energy technology with just about the highest public acceptance. But this very broad public acceptance can coexist with very local community opposition. And this especially occurs when solar power starts to conflict with nature, when it starts to cover agricultural land, or when it is too visible and too large in the landscape. And I see this in literature, but this also occurs and is increasingly covered by the media. And so I come to grid integration, another great challenge to the growth of renewables. And the grid historically was fed by these very large generators, thermal coal plants, gas, nuclear. And then the distribution grids took this power to lower voltage levels and to connection points that were exclusively set up for power demand. Now, we are also integrating more and more generation at these lower voltage levels, and this causes issues. To explain to you what the challenges are with grid integration of renewable energy, I want to take a step back and take a moment to explain in a few slides electricity. So let's consider the cable. A cable is a crystal structure of atoms. And through these atoms, charged particles, electrons, move around. Electricity then is a very organized movement of these charged particles from one region to another. This is direct current, in Dutch gelijkstroom, but we also have alternating current. And in alternating current, the electrons wiggle around. So electricity has a number of very important properties. One is the power. The power is the rate at which energy is transferred through electricity. Then there is the current. The current is really the amount of charges that is moving from one region to another. The more charges are moving, the higher the current. And you may remember from your physics classes in high school that similar charges repel each other and opposite charges attract, which means that there is a certain amount of energy associated with moving charged particles around when other charges are present. Voltage is then the electrical potential energy associated with each charge. All right. High current, lots of moving charges. High voltage, the charges have a large potential energy. There's a lot of push or pull associated with their movement. The power in alternating current is a function of both this voltage and this current and the phase difference between voltage and current, which is of less importance now. All right, I want to introduce another term, generators and loads. And to introduce the generator, I introduce Tadej Pogačar. Tadej Pogačar won the Tour de France. On his bike, he can push a lot of watts. And let's borrow his front wheel for a second. A generator is a device that converts another form of energy, in this case motion, to electrical energy. So what a generator does is really inject energy into the electricity system. A load, on the other hand, uses this electrical energy to extract energy and convert it in another form, in this case, light. So what is then our grid? Our grid is really a system or a device to transfer at a very large scale energy from generators to loads. And the grid is a bit of a lasagna of different voltage levels. And the grid can very much be compared with the road network. Just like a road network, there are highways for electricity transfer. And there are lines and cables through which a lot of electrical energy moves. And this is the transmission system. Just like a road network, there are also smaller roads for electricity that take electrical power to loads to remote villages and houses. And this is what is done by the distribution system. Now there's another similarity, and that is that every line, every cable can only take up so much power and transfer so much power. Just like roads can become congested and you have traffic jams, like the ring of Brussels. What is then the challenge of grid integration? Well, throughout the years, we have evolved from using our grid to take power from these very, very large generators to the lower voltage levels, which transferred it to exclusively loads, to a system that also accommodates distributed, scattered, smaller generators at the lower voltage levels. And our grid is transforming, yes, but it is not transforming fast enough to keep up. So we see issues emerge. We see that there are electrical energy flows in directions that they were not really going in the past. We see that cables and lines get overloaded, voltages deviating from their selected range, and unexpected costs for distribution and transmission system operators. And the result of this is congestion. Wind turbines and solar power systems cannot really connect anymore at the pace that they should. There are enormous grid queues, unprecedented levels. Worldwide, there is 2,500 gigawatts of renewable energy, large load capacity, and energy storage stuck in these grid queues. And this is huge. To give you an idea of how big this number really is, Belgian electricity demand hovers around 10 gigawatts, roughly. So this is an issue. This causes avoidable power curtailment, renewable energy not reaching the end user, avoidable greenhouse gas emissions, higher electricity prices, and this, as a result, weakens our European competitiveness. And in this context, the International Energy Agency recommends us to use the existing grid connections and the one we are building really to the max. We should use it as much as possible, the existing grid connections. And there's onshore grid development, but also offshore. At sea, we are also building connections. There are connections to connect offshore wind. They are also expensive. They are actually very expensive. But offshore wind is a very good idea. Offshore, at sea, wind turbines can produce much more electricity because there's stronger winds. Offshore also, in a country like Belgium, you can build a wind farm that you cannot really build anymore on land, let's be honest. And by now, this is a European industry that we can really be proud of. And we then also put solar panels on water. The answer is yes. Over the past years, we have seen floating PV develop. Floating solar power has by now reached almost technical maturity on very calm inshore waters, ponds, lakes, with not too much waves, not too much winds, but these systems perform, and they perform well. Because the underlying water can take up a lot of heat, solar panels can produce more power because they operate more efficiently. And we then also put these systems offshore at sea, and this is a bit more complicated. At sea, you have the promise of unlimited scalability. You can put much larger systems, but you also have to deal with the winds, with the waves, fatigue, corrosion, etc., etc. So these are costly systems. Wouldn't it be nice if we use the plots that are now reserved for wind power? Because you cannot go there with a container ship, you cannot go fishing there, you cannot go sailing there. These renewable energy zones offshore are reserved exclusively for offshore wind. Wouldn't it be nice if at these places where there's a lot of space and there are already grid connections, we also put solar power there? And this is the promise of hybrid offshore solar wind farms. So where am I going with this? I've now been talking for a while. I have established that we need a lot of renewable energy, and fast, to address climate change and to improve our energy security. I have established that grids, and especially densely populated regions, struggle to accept large solar power systems. There are grid connection queues, so it's becoming more and more difficult to connect renewable energy to the grid. And in this context, offshore floating PV offers a way to put large-scale solar power systems out of sight, where they are less likely to trigger public oppositions, at a place where they can connect to the grid. And this is really an exceptional value proposition in densely populated countries. Where else in Belgium or the Netherlands can you put square kilometers of solar power at a place where there is already a connection? So I come to my research question that I address in my PhD thesis. How can offshore floating PV electrically be efficiently combined with offshore wind in the North Sea? And I will use this diagram throughout the presentation a lot. In this diagram on the right, you see the wind turbines, you see the floating offshore solar systems, you see the array cables that connect the wind turbines now, you see the offshore substation, and what the offshore substation does is step up the voltage from the array cables from 66 or 33 kilovolts to 220 kilovolts for efficient power transfer. Export cables then take this power to a connection point onshore, on land, and the onshore substation connects the whole thing to the onshore grid. So, let me have a sip of water. I have my research question, and I address this question in a number of chapters. Chapter 2, I look at wind resources and wind power modeling. In chapter 3, I look at solar resources and solar power modeling. In chapter 4, I then look at how solar and wind power behave relative to each other. In chapter 5, I answer the question whether solar and wind power generators can really use the same export cables. In chapters 6 and 7, I then want to know the internal grid. Are there any showstoppers there? Can we also connect solar power in the internal wind power connection grid? In chapter 8, I want to know about the money. How much can we earn with offshore floating PV if we integrate it with offshore wind? And then finally, in chapter 9, I look ahead towards more future technologies, more fundamental approaches to boost the yield of offshore solar power systems. Let me skip to chapter 4, where the first results are. I'm interested in the complementarity between solar and wind power in the North Sea. Complementarity is really the relative behavior of wind and solar resources compared to each other. And so I look at two parameters, the strength of sunshine at sea, and then also the strength of wind power at the hub height of modern wind turbines. Why am I interested in how they behave relative to each other? Because in theory, when wind power is strong, we could use the grid for its original use, what it is designed for wind power transfer. But when there's not much wind and a lot of solar power, maybe we could use the same grid for solar power transfer. And so I have a look at the complementarity with a metric called Kendall-Stowe. Now, Kendall-Stowe tracks two time series, wind and solar power. And the important thing to remember is that it gets a value between minus and plus 1. Kendall-Stowe of -1 means that if wind power goes down, solar power always goes up, and vice versa. Kendall-Stowe of 1 means that they always move together. So if solar power would go up, wind power always goes up with it. These are the numerical results for the Belgian North Sea. What you see here is that indeed there is solar-wind complementarity in the North Sea, but it is mainly so at the longer timescales. So especially at seasonal timescales, that is where solar-wind complementarity occurs. Much less so if I look at hourly, 10-minute, or shorter averages. Moreover, this is a dynamic that doesn't occur everywhere around the world if I compare this with literature values. So graphically, it looks like this. Throughout the year, wind power really starts out strong. Very gradually, it alternates its strength with solar power resources. Very gradually, the strength of solar power grows towards the summer, while wind power weakens, and then the opposite dynamic happens towards the end of the year. And if you live in Belgium, you know, okay, the summer is quite sunny, the winter is quite windy, but it's really this gradual alternation between wind and solar power that is surprising. And this occurs throughout the entire historical data that I looked at from 2011 to 2018. With a lot of variability, yes, but the baseline complementarity returns. Year after year, solar and wind power alternate their strength on seasonal timescales. But I have talked about climate change, and climate change will very much impact planetary dynamics, and so also renewable resources. So I wanted to know, if we look ahead with climate projections, do we see the same pattern? And the answer is yes. Even under very severe climate change, we see this pattern returning up until 2100. So we can count on this phenomenon not only to occur now in the coming years, but also in the future. And the conclusion that I draw in this chapter is that significant solar-wind complementarity exists on weekly and monthly timescales, much less so on shorter timescales. And we can count on this phenomenon to continue. Now for the technical implications. Can we effectively use the same cables, knowing that the strength of solar and wind power alternates like this? This is a question that I answered in chapter 5. To do this, I used my characteristic charm and a lot of patience to ask Elia for grid data. I got finally grid data on some export cables in the Belgian North Sea. And I knew how these cables are operating, what their specifications are. These are quite big cables. They're very strong cables. They are buried anywhere between 2 and 11 meters below the seabed. And when you buy them from a manufacturer, you get a rating, a static rating, and you know, if I stay below this rating, if I respect this number, everything will be fine. But I'm interested in the true potential. I want to know how far we can push this cable without violating any limits. And the real limit on how much power this cable can transfer is set by the conductor temperature. Now, the conductor temperature, these big cores of aluminium, if they cross 90 degrees, then the insulation around them starts to degrade. So theoretically, we could push a lot of power through the cables until this temperature is reached, but then we have to slow down and stop. So we can operate above this static rating as long as we respect the temperature. And the cable temperature on its turn is related to the current and the power flowing through the cable. So more power through the cable, higher temperature, more heat. I have these specifications, and I could use these specifications to, with a thermal model, simulate the thermal behavior of this cable. What I see with the specifications from ELIA and this thermal model from literature is that these cables have a very, very big thermal inertia. The time constant, more than 4 days, and this is the time it takes to reach about 63% of the maximum temperature with nominal power. So big thermal inertia. Then I look at the cable's temperature throughout the year. What I see is that over a period of 2 years, I see my complementarity figures return. I see that, okay, in winter, these cables are used very well, close to their limits. They transfer a lot of power. But during summer, there's much more margin to transfer more power, which means that these cables could transfer more power exactly when solar power could produce most electricity. So this is a big promise. What would happen if I integrate and simulate the integration of solar power with roughly 1 gigawatt of offshore wind? So I matched the power capacities. I looked at how the cable would behave if I integrate 1 gigawatt peak of solar power with this 1 gigawatt of offshore wind power. And I see when I do this, first, much more power is transferred through this, I might add, very expensive cable. And so the promise is that we could spread the costs of this equipment over a much larger volume of renewable energy. And we see that, especially in summer, more power is transferred, and so this cable gets a much more consistent loading throughout the period of 2 years that I simulated. Okay, but you saw also that sometimes I get very close to the 90-degree limit. And at a certain point, if I would just send all solar and wind power through these cables, they would overheat. So I make the decision to curtail power. And power curtailment is a bit like turning down the tap so that your sink does not overflow. Power curtailment avoids that cables are overloaded and overheated. And I make the very conscious decision that if power needs to be limited, first I curtail solar power and only then wind power, because the wind power was there first. And solar power is very unlikely to be integrated if it would hinder the transfer of wind power. So when curtailment needs to happen, when power is available, but I cannot send it through these cables, I curtail solar power first and only then wind power. And the amount of power that is curtailed is the curtailed power. Now, what I see over this 2-year period is a number of things. I see that a lot of solar power can be transferred through those cables without violating the thermal limits at all. You see that the 90-degree limit in the bottom figures is always respected. And what do I conclude from this chapter is that you can send a lot of solar power through the offshore wind grid. Give you a takeaway number, matching the powers, so integrating 1 gigawatt peak of solar power would increase the power transfer by 36%, and this is the electricity demand of about 310,000 Belgians. So this is a lot. All right. It's not only the complementarity that makes it happen, it's also very much the thermal inertia of these cables that enables this very large transfer of solar power. Now I'm interested in the internal grid. Are there any showstoppers in the array cables that connect the wind turbines among themselves or in the substation? And where would I best integrate my solar power? At the wind turbines furthest from the substation, closest by, or somewhere else? This is what I answered in chapters 6 and 7. And to do this, I again had to make use of my characteristic charm and a lot of patience to again obtain industrial data that power producers do not really like to share. And this is the reason why I blurred the single light diagram. You cannot see the values. Okay. The nice thing about this case study is not only that it is a very modern grid, 15 megawatt turbines and a 66 kilovolt power collection grid, but also that I modeled the wake effect. And this is important because I did not just aggregate the power of all the wind turbines, I modeled the power production of each individual wind turbine of this wind farm. And this is important because they lose a lot of power to the wake effect. Why is this important? Because the cables that connect the wind turbines are loaded differently when more or less power is transferred through them. So this is an important effect to take into account. All right. Together with my colleagues, Giacomo Bastianel and Kaan Yurtseven, I then developed a methodology to optimize the distribution of these solar systems in the offshore wind grid. First, we develop scenarios that make use of wind and solar power data, also the demand of the surrounding grid. We make use of stochastic generation expansion planning based on DC optimal power flow simulations, and we then evaluate the performance of the combined solar wind system with a time series and an optimal power flow at high resolution, 10-minute resolution. And these are the numerical results, and a couple of things stand out. First thing that stands out is that there are no showstoppers in the internal wind power collection grid. There are no constraints that make it impossible or very difficult to transfer solar power. However, here, as opposed to the previous chapter, much less power is transferred. And this is a result of two dynamics, or two things. First, here we had to use the static ratings of the cable, so we could not use dynamic thermal rating. But also, these modern wind turbines, 15 megawatts, have such good capacity factors, such good performance throughout the year, also in summer, that the gap in the connections that offshore PV could make use of for free becomes much narrower. And I'm also interested in what triggers all this curtailment. So in this figure, I plot the power production of solar and wind power together in the red line on top, and wind power alone in the blue line on top. And for the same time steps, I plot wind power curtailment at the bottom in blue, and different amounts of solar power curtailment for different capacities in shades of red at the bottom. And I see that most curtailment happens actually when the power production crosses the ratings of the export cables, the ones that connect the offshore substation to the onshore grid. However, the array cables, just like in the previous case study, show a much more consistent loading. On long time averages, in the figure on the left, monthly, and on short time averages, in the figure on the right, 10-minute averages. Okay, I know that the equipment can be used much more efficiently. I know where the constraints are. How does this translate to an optimal distribution of PV throughout the wind power grid? And here the results are quite surprising, because taking into account the wake effect, I would have expected that the optimizer avoids the strings where most wind power is transferred. But this is not really the case. Precisely because the export cables are the bottleneck in the system, the distribution of solar power throughout the internal grid does not really matter that much, because most curtailment is triggered downstream anyways. So connecting offshore PV and the offshore wind grid offers also a bit of freedom. We can take other things into consideration, knowing that the majority of curtailment is triggered by the substation and especially the export cables anyways. So we can optimize for losses or reliability, and this leads me to my guidelines, in which I recommend that offshore PV is best connected directly to the substation or to the wind turbines closest to it. All right. In this chapter, I have learned where to connect offshore PV, what the constraints are. So, have I found a way to integrate gigawatts of solar power through grid connections that are already there or not? And until now, the results are quite promising. Because I have shown that we can transfer an enormous amount of solar power through connections that were exclusively designed for offshore wind without violating any limits. So this is very promising. Let's then look at the economics. Look at the economics, we simulated the integration of this combined solar wind system with the Central Western European grid. So the Netherlands, Belgium, France, and Germany. We simulated in a scenario of the NSOE, which is the European Network of Transmission System Operators, how much money you could earn with the solar power in this connected wind farm. To do this, we made use of the DE 2030 scenario. And this is a scenario in which Europe really takes control of its energy security, goes for energy autonomy through renewables, and as a result, a lot of solar and wind power get integrated in the system. Now, revenues tell you something, but I really want a tangible number to show how much or how little this is. So what I'm really interested in is how much can the solar power cost to not make a loss? How much is it allowed to cost to break even on a 25-year lifetime, such that it does not run a profit, but also does not run a loss? How cheap does it have to be to not get in trouble in the market? Here the results are quite sobering. The results are between 390 and 436 euros per kilowatt peak. And this is about half what it currently costs to build a large solar power system on land. So by 2030, we should figure out how to make offshore solar systems cheaper than what they currently are onshore. And this is very unlikely, if not to say completely unrealistic. So these results are quite sobering and do not look good. What is the driving dynamic then? Cannibalization. Cannibalization means that solar power systems across different countries all produce electrical power at the same time. So when they can earn money, they do so at a time when there is a lot of supply and typically also not that much demand. And this puts a lot of pressure on the prices and on the money they can earn. So cannibalization is a problem for all solar power systems, but it's especially so for offshore PV, because you have challenging costs and a challenge at the revenues. And to make money, you want exactly the opposite. So I asked myself, well, we are developing offshore grids for offshore wind power to take this wind power to different countries and take the power to where it really needs to be. Maybe these offshore grid connections can also give the solar power access to more demand and higher electricity prices. However, literature shows that this will really not be the solution, because solar power is so well correlated also across neighboring countries, also across countries that could be reached by these interconnectors. This will not really solve the issue of cannibalization. And moreover, with hybrid interconnectors and market designs that are currently on the table to facilitate the development of a true North Sea grid, these ideas will probably make it worse. So is this a solution? Not really. The only solution that may remain is energy storage. And I'm not the first to say that solar power needs energy storage. This is not really an original conclusion. But what my results do is re-highlight the importance of energy storage. And I argue that maybe because you can build such a large system offshore, with solar and wind power and energy storage centralized in one plant, maybe we have a chance at making such big systems that we can offer the inertia that is currently being phased out of the system by these very large plants. Because offshore, you can build at a scale that is no longer possible onshore. So maybe there are new revenue streams there. So I learned in this chapter that the economic outlook for offshore PV is really not good. And I have to be honest about the technical potential, but also about the economic outlook. And in offshore grid development, there's clearly tension between lowering consumers' electricity prices, which is of course good, but these same measures can also put more pressures on producers, which then not really encourage them to invest in offshore renewable capacity. So this is an important tension. And then in chapter 9, I look ahead and I ask myself, okay, could there be other methods or other technologies that could play a role in the future of offshore solar power and boost its yield? And notably, I have a look at the role of DC in power collection grids, but also maybe integrated heat engines. Because with solar panels, you produce a lot of heat as a side effect, and you do so above the sea, which is really an enormous heat sink. You can transfer a lot of heat to the sea without raising its temperature. And my chapter conclusions here, I go over them a bit faster, show that DC has a lot of potential, but it's really the lack of adequate step-up converters and protection devices that makes it difficult to implement. However, it could also reduce losses at in the future and get more power density in the system. So it is really promising. And for thermoelectrics and integrated heat engines, I calculated physical potential, but I also argue why it will be very hard to implement the technologies to use this. And so I come to my conclusion. I said that my research question was, how can we efficiently electrically combine offshore PV and offshore wind in the North Sea? And through my work, I have developed a number of guidelines. I know where to connect the solar power. And I also show very much that seasonal solar wind complementarity helps to use the same cables, the same offshore infrastructure for both wind power and for solar power. And we can count on this phenomenon to occur now, but also in the future under climate change. And it's not only solar wind complementarity, but also very much the thermal inertia of this equipment that helps to transfer a lot of solar power through the connections that were originally exclusively built for offshore wind. So like this, really gigawatts of solar power could be integrated in the offshore grids that are already there, that we are building for offshore wind, and that we will build in the future. However, we also have to be honest about the economic results, and the current economic outlook is really not good, with high costs and low revenues. So where will we end up? I wonder how much offshore PV will be in the system by 2050, and there are a number of forces that can tilt the balance in favor or against offshore PV. And these forces can become bigger or smaller. I cannot predict them. What I can say is that offshore PV really offers scalability that is unique, and it's precisely when you have a scarcity of suitable connection points and a scarcity of suitable space, that is when offshore PV can play a role. All right. In this work, I published a number of papers, which I based my PhD on, and these are then listed. I also had the privilege of attending some conferences, and of course, I have some remaining questions. I wonder if you could calculate all the costs associated with solar power integration, including grid connections, including energy storage, across the stakeholders for agri-PV, or also building integrated PV, or rooftops, or offshore PV, how would these different implementation modes compare and also evolve over time? I also wonder, being very impressed by the results of dynamic thermal rating, whether we can integrate it at different layers of the system, also in energy management systems. And finally, the investments that we need to build renewable powered grids are really gargantuan. They are massive. And so we really need to develop methods and mechanisms that fairly distribute the costs and the benefits to lower the hurdles to make these investments happen. This is more of an economical and a social question. So I thank you for your attention, and I very much look forward to your questions.